So we're going to continue our discussion of electrophilic addition reactions and look at which product do we get more of and see how do thermodynamics and kinetics compete to give us different products depending on the conditions. So in the electrophilic addition of 1,3-butadiene, whether we get the 1,2 product or the 1,4 product is highly dependent on temperature. At low temperature, we get primarily the 1,2 product, whereas at higher temperatures, we primarily get the 1,4 adduct. So let's see if we can explain this difference and then use that in an example. So first, let's consider the reaction energy diagram for this electrophilic addition and the difference between our two products. So the first step, regardless of which product we make, is the same. We get the proton transfer to make our carbocation intermediate, and they're just showing one of the resonance contributors here. Of course, the other resonance contributor, the double bonds moved over to here, and the positive charge is here. The difference between the two products is what happens in the second step, the nucleophilic attack. You can see that the transition state for the formation of the 1,2 product is lower than the transition state for the formation of the 1,4 product. And you can also see that the 1,4 product is more stable than the 1,2 product. And so if kinetics control the reaction, then we're looking at how do the reaction barrier heights influence the formation of the two products. Because the activation energy for the 1,2 product is lower than the activation energy for the 1,4 product, this reaction is going to happen more quickly. So we would say that the 1,2 adduct is kinetically favored. It's going to be formed faster. And it turns out that's favored at lower temperatures, and we'll explain why that is in the next couple slides. The 1,4 adduct, being more stable fundamentally, is thermodynamically favored. And so if we didn't have to worry about how long it took to form them, we would tend to form more of the more stable product. And so that's what we mean by being thermodynamically favored. So if it's formed faster, it's kinetically favored. If it's more stable, then it's thermodynamically favored. Now, as far as why the 1,4 adduct is more stable thermodynamically, if you remember when we first introduced alkenes, we talked about which alkenes were more stable. And the more substituted an alkene, the more stable it is. And so this alkene just has one carbon coming off the carbon-carbon double bond, whereas this one has two. So that's why the 1,4 adduct is more stable. So the reason high temperatures favor the more stable product is because we can establish an equilibrium. Right? We might form the 1,2 adduct, but at higher temperatures, there's more energy in the system, and so it's likely that the bromine can pop back off and reform that carbocation intermediate. And so if we can form this sort of equilibration, then that's always going to favor the more stable product because even though we might form the less stable one faster, it'll go back and form the carbocation intermediate, and then it's got another chance to form the more stable product. And even if it forms the less favored one again, as long as you run the reaction for long enough, eventually we'll form more of the more stable product. So at higher temperatures, when there's more energy in the system, and it's more likely to form this equilibrium between the products and the intermediate, then we're going to favor the more stable product. So higher temperatures tend to form the more stable product. All right, now why would the 1,2 adduct be formed more quickly? So first I'll give you the book's explanation, which I actually don't love, and I'll give you what I think is maybe a better explanation. So the reason the book says the 1,2 adduct is formed more quickly is because the hydrogen's adding to position 1, so the bromine is already fairly close by, and so when it sees a partial positive charge on that carbon 2, right, it sort of jumps right in and is formed more quickly. Then it's got to move farther in order to see the partial positive charge on carbon 4. And so the book argues that this proximity effect makes the formation of the 1,2 adduct faster. And so at lower temperatures, where we are less likely to form an equilibrium, where once we form the products, they're done because there isn't enough energy for that bromine to pop off and go back and form that carbocation intermediate. So lower temperatures favor the product that you're going to form more quickly. So let's look at an alternate explanation besides this proximity effect. So if we consider this intermediate, this carbocation intermediate, right, it's resonance stabilized. And so it is composed of contributions from both of these resonance structures. When the bromine attacks here, that's going to form the 1,2 adduct. And when we form this transition state, right, as the bromine comes in, right, we're essentially going to collapse the two resonance structures. And so the transition state is going to look more like this resonance structure where we have a secondary carbocation. Right? When the bromine attacks here, we're going to have the transition state for that process is going to look more like a primary carbocation. And we know that a secondary carbocation is more stable than a primary carbocation. And so for that reason, the transition state for the formation of the 1,4 product is higher than transition state for the formation of the 1,2 product. And so the reason we form the 1,2 product faster is because its transition state has a more stabilized carbocation, and that's going to lower the energy and make that reaction faster. In either case, lower temperatures favor the product by kinetic control, and it's going to favor the one that forms faster. So whether you use a proximity argument or this lower activation energy argument, I would accept both. I think this is a better explanation, but because the book just gives the proximity one, if I were to ask you for an explanation, I would accept both. Okay, so let's finish off with an example. So we want to predict the products of the following reaction and then determine which will be the major product. Now, in the last video, we had an asymmetric molecule that looked kind of similar to this one, and so we had to be more careful and draw out all of our possible carbocations. I think in this case, it's a little bit easier because this one is symmetric, and so I don't need to draw all of them out. Let me give ourselves a little bit more room again. Right, and so whether I add the hydrogen here or here, I'm going to get the same two products because the molecule is symmetric. So I'm just going to imagine adding the hydrogen here. Right, and so when I do that, the carbocation that's going to form is that one. And then, of course, we have a resonance structure. I'm not going to put the arrow in to keep things cleaner, right? But to get the resonance contributor, we're going to move that pi bond over, and the carbocation is going to end up down there. All right, so if I consider this resonance contributor, the bromine in the product is going to add there. So I have one of my products is going to be that. And if the bromine adds to this resonance contributor, it's going to go down there. So my other product is there. So between these two products, I want to decide which one is going to be the major product. So first I want to think about stability. So here I have a tri-substituted alkene. Here I have a tetra-substituted alkene. So this one is the one that's going to be more stable. So this would be favored under thermodynamically, under the thermodynamic control, and so at higher temperatures, and so we were using 40 degrees as higher temperatures, should favor this one. Right? And I would argue that this one would be favored kinetically and be favored at lower temperatures because, right, when the bromine adds here, our transition state is going to have what is approximately a tertiary carbocation, which is more favorable than adding here, where our transition state is going to have what is largely a secondary carbocation. So at lower temperatures, we would have favored this product. It would be following the kinetic control, but because we're at what the book uses for higher temperatures, we're going to form the more stable product, and so this one is going to be our major product.